Hey guys, today I want to present a solution for the USAMO Math Olympiad 2022 problem 4. At first, let's have a look on the problem statement. We should find all pairs of primes, p and q, such that p minus q and pq minus q are both perfect squares. So we can write p minus q is equal to a squared and pq minus q is equal to b squared. And here, a and b are both integers. So in such problems where we have primes and should find all of them, it's always a good idea to make some factorization. And therefore, we will try to factor this one because we have a common factor q in it. So we can write p minus 1 times q is equal to b squared. From this, we know that q divides b, but this is not too helpful yet, so let's have a look what else we can do. And if we have a closer look on these two equations 1 and 2, we see that both times we have a minus q on the left hand side. And therefore, maybe it's a good idea to subtract these equations from each other to get rid of this q. So let's do q minus 1. And we have pq minus p is equal to the right hand side b squared minus a squared. And this equation is nice because on the left hand side we have a common factor p, so the left hand side can be written as p times q minus 1, and on the right hand side we have a difference of squares, and therefore we can write the right hand side as b minus a times b plus a. And now we use the fact that p is a prime, and therefore we know that p must divide one of these factors. So p divides b minus a, or p divides b plus a. Now it would be nice if we can eliminate one of these cases, and therefore it's a good idea to do some bounding. At first, notice that since a squared is not negative, we know that p is greater than or equal to 2. And now, if we have a look on this equation, we get that b squared is equal to p minus 1 times q, and this is strictly less than p squared. And thus, we get that p is larger than b, and since b minus a is less than or equal than b, p is larger than b minus a, and therefore this case is not possible. So we have this case. So let's have a look on the case that p divides a plus b. As I already said, it's always a good idea to make some boundings. And since we already figured out that p is greater than b, maybe it's a good idea to find some relation between p and a. Therefore, we take equation 1, and we know that since q is positive, that p is greater than p minus q. This is equal to a squared, and this is clearly greater than or equal to a. So we also know that p is greater than a. Therefore, a plus b is less than p plus p, and this is equal to 2. But now, since p divides a plus b, and a plus b is smaller than 2p, p must be equal to a plus b. Now, we can have a look on our equation 3, and we have the factor p on the left hand side, and the factor b plus a on the right hand side. And since they are equal, they cancel out. And so q minus 1 is left on the left hand side, and b minus a is left on the right hand side. And therefore we know that q minus 1 is equal to b minus a. Now, if we subtract these equations from each other, we get that p minus q plus 1 is equal to 2 times a. Now we can have another look on these equations here, and we see that we already know what p minus q is, because p minus q is equal to a squared, so we can write here a squared instead of p minus q, and therefore we have a squared plus 1 is equal to 2a. If we now bring the 2a onto the left hand side, we have a squared minus 2a plus 1 is equal to 0, but the left hand side is also a minus 1 squared, so a minus 1 squared is equal to 0, and this means a is equal to 1. Now with a equals 1 we are almost done, because from equation 1 we get that the difference of two primes is equal to 1, so p minus q is equal to 1, but this is only possible if p is equal to 3 and q is equal to 2. The last thing we have to do is to prove if p is equal to 3 and q is equal to 2 works for our equation 2. So let's put in 3 and 2, and we get 3 times 2 minus 2 is equal to 4, and this is indeed a perfect square. So PQ is equal to 3, 2 works, and this is our only solution.